So for this FRQ, it says the figure above shows a graph of the piecewise linear function of f for the closed interval of from -4 to 12 of the function g is defined by g of x equals the integral from 2 to x of f of t dt. And for part 8, it asks, does g have a relative minimum, a relative maximum, or neither at x equals 10, and to justify your answer? And the answer for this is the graph of g of x has neither a maximum or a minimum at x equals 10, since g prime of x equals f of x, and f of x is negative from 8 to 12. And for this part of the FRQ, most students get it wrong because they don't know what the graph is actually showing. And the graph is actually showing that f of x equals g prime of x. It's the same thing. And that's stated by the second fundamental theorem of calculus. And another important thing for this part of the FRQ is that you have to know that the derivative of the function, which is g prime of x, is a maximum when the sign changes from positive to negative, and when it's vice versa, when it's going from negative to positive, it's a minimum. So in order to get the points for this FRQ, you have to state why it is that this is true, and so you have to say that g prime of x equals f of x, so that's your first point. Your second point comes from your explanation or your justification, which in this one would be f of x is negative from 8 to 12.
All right.
Okay, so for the second part of this FRQ, it asks, does the graph of g have a point of inflection at 4, and justify your answer? The answer for this section is the graph of g of x does have a point of inflection at x equals 4, since g prime of x and f of x is increasing from 2 to 4 and is decreasing from 4 to 8. So this kind of goes on continuation with the fact that g prime is the same as f of x, which is shown in the graph. And for this problem, you have to keep in mind that concavity deals with g prime of x when it's increasing and decreasing instead of the sign changes. So instead of going from negative to positive, it's going from increasing to decreasing. And that's a common misconception for this portion of the FRQ. And in order to get the points for this FRQ, you have to lay down your answer, which would be that it does have a point of inflection at x equals 4, and your justification is also part of that point. So you have to name again that g prime of x is the same as f of x, and you have to say why. So when it's increasing from 2 to 4 and then decreasing from 4 to 8, that would be your justification. So for this part of the FRQ, you only get 1 point, and you have to do both parts in order to get the point.
Okay, so for part C, we have to find the absolute minimum value and the absolute maximum value of g on the interval from 4 to 12 and justify our answers. So the first thing we need to do is take the derivative of g prime, which we take the derivative of our function for g, which is just that integral. And the way you do that is it's just a function. It's the derivative of an integral is always just a function. So once we have our derivative, which we know is the function, we look for sign changes in the derivative because that's always, we need to find our critical points to test. So the only time the derivative changes, which we know is f, is when the sign of f changes, which happens when x is equal to -2 and x is equal to 6. So those are our critical points that we will be testing. And the other points we need to consider would be the endpoints. So when x is equal to -4 and x is equal to 12. So we can make a table of all of them. These are our endpoints where x is equal to -4 and x is equal to 12, and these are our critical points where x is equal to -2 and x is equal to 6. To find g of -4, we'll have to plug in -4 into the equation they gave us, so we get the integral from 2 to -4 of f of t is equal to, and there's no mathematical way to do it. You have to know that you're looking at that point there, and then you take the area. and there's -4 and 8, they add up to +4, but because the smaller number is up top, it becomes negative, because it's always, in a normal integral, it's going to be the smaller number on the bottom, the bigger number up top. But because it's like that, that's why this one's negative. So g of -4 is 4. And here, we plug in 12, so we have to take the integral from 2 to 12 of f dt. So we're going to take the area from 2 to 12, so 8 minus 8 minus 4 leaves us with -4. And it's just -4 because the bigger limit was up top. And then we gotta test our critical points, which the process is the same. So g of 2, you plug in -2 up top, and then because it's the smaller number, you take the area from 2 to -2, which is 8, but you negate it because the smaller limit was on top. And for g of 6, you plug in 6, so you take the integral from 2 to 6 of f of t. So the area from 2 to 6, so 2 to 6 was just 8. So g of 6 was 8. And then we look at our table, and we know this is going to be our absolute minimum when x is equal to -2, and our absolute maximum occurs when x is equal to 6. Because that's the biggest value, that's the smallest. So from all that, you would make a statement, something like this. On the interval from -4 to 12, the absolute minimum value is g of -2 equals -8, and the absolute maximum value is g of 6 equals 8. And and the points are awarded by 1 point comes from your endpoints, so from considering -4 and 12. And another point comes from your critical points, such as x equals -2 and x equals 6. And the other 2 points come from the answer with justification. So stating that this was the absolute minimum and this is the absolute maximum, that would count for one of the points made, because that's the answer, and the justification the table itself should be another form of justification and all your calculations. But it's important to make the statement that this coordinate is the absolute minimum and this one is the absolute maximum.
So for question D, we are being asked for -4, when -4 is less than or equal to x, and that is less than or equal to 12, we need to find all the intervals for which g of x is less than or equal to 0. So with this particular question, we have to continuously reference the previous question, which Emilio explained earlier, and that is due to the fact that we had derived values for the critical points and plug that into the original equation, which was given to us, g of x equal to the integration of f of t dt, and that's x to 2. And the reason why this is important is because after we find the values of the critical points, we plug them into that particular equation, we're able to see where g of whatever number we plugged into the equation is equal to 0. And this again is important because we want to know where g of x is less than or equal to 0. So after plugging those values into the equation, I expanded the values a little bit more, so we had all of the critical points, and I found that g of 2 is equal to 0 and g of 10 is equal to 0. So we must keep in mind that due to the fact that these values are equal to 0, they will either be the beginning or the end of the intervals that we find g of x is less than or equal to 0. So once we've done that, we have to go back to our graph once again and find where the values actually remain negative. The reason why this is important is because, again, less than or equal to 0, so the values that are going to be within these intervals have to be negative. And from -4 to 2, we see that -4 goes to -8, and then it goes to 0, so we know that there our values are going to remain negative. And then, moving further down the graph, we check 2 to 6, 0 to 8, of course, you're only gonna have positive numbers within those two numbers. And then 6 to 8, 8 to 0, you are gonna be going down. You are gonna be decreasing the value of the numbers from getting from 8 to 0, but they're not any negative numbers. There are no negative numbers between 0 and 8. So continuing from there, we check 10 to 12 and 0 to -4. From 0 to -4, you will most definitely have to go into the negative spectrum of numbers. So you're gonna have to consider that at this point, from 10 to 12, the values are all going to remain negative, and from -4 to 2, all the values are gonna remain negative. So you kept in mind that 2 was our most important number, as well as 10. And you find that when g of x is less than or equal to 0, it is for -4 when that is less than or equal to x, which is less than or equal to 2. And this is going to give you 1 point. The entire integral equation, one of the integral equations will definitely give you 1 point. And then when 10 is less than or equal to x, which is less than or equal to 12, that will give you another point. So in total, question D is worth 2 points. And common errors that students make in this particular question actually goes back to the question C. If you do not determine which critical points are the correct critical points, the values that you are going to derive as a result of plugging in your x values into this integration equation are not going to be correct. So say you put in, I don't know, -3 or something, and that gives you a positive number, and that positive number gets subbed in and is put here in between -4 and 0. Now you have a conflict. It would no longer be continuously negative from -4 to 2, there would be an issue, and so on throughout the rest of the x value equations. Another thing that I would like to note in this particular equation is that not only are the critical points the most important thing, but being able to make sure that you do not confuse your original equation with trying to find g prime of x. You are only looking for g of x and nothing else, and that is question D. Hi, so there's actually another approach to part D on this particular free response question. Again, we're being asked to find all the intervals at which g of x is less than or equal to 0 for this particular graph, and it goes from -4 to 12. And to solve this particular problem geometrically, we have to consider two definitions that we found when we were studying Riemann sums and definite integrals. The first definition is that if f is defined at x equals a, then from a to a, f of x of d of x, f of x times d of x is equal to 0. And the second definition is if f is integrable on a, b, then b to a of f of x of d of x is equal to negative a to b f of x d of x. The reason why the first definition is important is because when we are referencing the original graph, we find that g of 2 is equal to 0 and g of 10 is equal to 0. This again is important because we are finding where g of x is less than or equal to 0. Now, we need to also focus upon this. We are going to consider all of the areas that are within this particular graph. So we're going to look from 2 to -2, 2 to -4, 2 to 6, 6 to 10, and 10, and so on. So by plugging the values of 2 and -4, for example, into the original integral equation, when we are referencing the second definition, as I told you guys about, we have to remember to flip the sign. So even though the equation is written as such, 2 at the base and x atop, because we are putting a negative value in for x, this doesn't work. You have to flip the signs. So then it would become instead -4 to 2 rather than 2 to -4, because that doesn't make any sense. But because we cannot have a negative value at the base, the negative has to come out. And once you have calculated the area by using these two values, you apply the negative sign. So you know that going from 2 onto -2 and -4, it all remains negative. So you know that from -4, when that is less than or equal to x and less than or equal to 2, that g of x is less than or equal to 0 the entire time. So that will get you 1 point. Now we continue on and look between the values of 2 and 10. So once we put the values of 2 to 6 into this particular equation, so if we put in 2, 4, 2, 6, 2, 8, any of those values, we find that the area remains positive. And even though this value is going downwards, which would make it negative, because we are only concerned with positive values and we look at both areas in the end, 8 plus negative 8 cancels out and is 0. So from here, we know that there is no point at which g of x is less than or equal to 0. It may have been equal to 0, but the values are actually greater than 0. Next, we apply it to our second 0, which was 10. So from there, we would put 2 to 10. Actually, no. Yes, we would consider 2 to 10 as well. And we have to look at the fact that the values that we would derive as a result of plugging in the value 10, it would remain consistently negative because we again had to flip the signs. And that is our D.